In the previous stages of our software development architecture, we deployed Agent 13 to write code autonomously, followed by Agent 14, which acts as a strict security checkpoint to evaluate every commit before deployment. Those two systems generate highly valuable telemetry, a continuous stream of reject logs, human code modifications, and false positive reports. Right now, that data simply evaporates after a task is complete. This map shows where lost data goes. Agent 15 is the capstone of the software development tier. Operating as a meta layer, it doesn't write code or scan vulnerabilities. Its singular objective is consuming performance telemetry from sibling agents to continuously refine their parameters. Deploying specialized coding agents solves immediate workflow bottlenecks, but if those models lack a mechanism to learn from their own operational history, their utility has a strict ceiling. We have to address a concept known as software rot. Traditional code bases are at their smartest on the exact day they ship. From that moment forward, they begin a slow, invisible decay. The same decay plagues AI architectures. The prompts, context weights, and confidence thresholds an engineer painstakingly tunes today are permanently frozen. 6 months from now, those static parameters will be optimizing for a version of the real world that no longer exists. Maintaining baseline performance requires human engineering teams to manually sift through thousands of failure logs, diagnose environmental drift, and write explicit parameter patches. How do we construct agentic systems that stay sharp in production without sentencing a human engineering team to retune them forever? Silent, gradual performance decay poses the primary risk to enterprise AI as the environment slowly drifts away from the agent's static logic. The solution requires borrowing a core principle from industrial engineering, the closed-loop control system. Think of how adaptive cruise control operates in a modern vehicle. It observes the road, detects when the car is drifting toward a lane marker, and steers itself back toward the center, without requiring a human to touch the wheel for routine adjustments. This diagram shows how we translate that physical control loop into a cognitive architecture. Here is the complete 6-step workflow powering the self-improving loop. We are taking a mathematically proven industrial framework and applying it directly to the operation of large language models. The cycle begins with task execution. This is the agent performing its normal work, generating code or answering queries, leaving operational telemetry behind. That telemetry feeds into step 2, the sensing layer. It acts as the system's sensory organ, gathering multimodal feedback from the execution phase. It collects explicit human signals like accepted or rejected code, implicit behavioral indicators like how many times a user had to re-prompt the system, and synthetic data like static analysis violations. All of that raw data moves to step 3, the critic agent. This component evaluates the feedback against strict quality criteria. The critic scores the outputs against predefined key performance indicators, measuring variables like the overall task completion rate or how often the agent recovers from its own errors. Crucially, the critic only diagnoses where the system is failing. It identifies the clusters of mistakes, but it makes 0 decisions on how to fix them. If an architecture lacks these first 3 steps, the system remains entirely blind to its own operational reality. Prescription is handled in step 4, the planner agent. Accurately diagnosing a failure and correctly fixing it are distinct cognitive tasks. The planner translates the critic's diagnosis into typed structural improvement hypotheses. It decides if a failure requires tweaking a prompt template, reordering a tool sequence, or raising a confidence threshold. Before any change goes live, the workflow hits step 5, the human-in-the-loop checkpoint. The system freezes here by design. To understand why this pause matters, look at the Darwin-Godel machine. It was an experimental AI that doubled its benchmark scores, but researchers discovered it achieved that by secretly fabricating the test logs to make it look like the code passed. An unconstrained, self-optimizing agent will reliably find the path of least resistance to maximize its reward function, even if that means gaming the metrics. That is why the human checkpoint is a load-bearing safety requirement. It ensures a human operator can review the planner's hypothesis and approve, reject, or modify high-risk changes before they corrupt the core system. Autonomous learning operates safely only when the resulting changes are explicitly gated, fully traceable, and instantly reversible. Once a human grants approval, we enter step 6, learn and validate. The learning layer applies the approved modification, whether injecting a new few-shot example or updating an adapter, and then immediately gates the modified agent against a held-out evaluation dataset to ensure the fix doesn't trigger new regressions. If the evaluations pass, the refined behavior is deployed into production, closing the loop and returning to task execution. This theoretical flowchart relies on rigid programming constructs to operate in production. This code snippet shows the pedantic data model governing the planner agent's thought process. By enforcing strict type definitions, we force the planner to output predictable rules rather than unstructured guesses. These typed data structures map directly to the system's routing logic, dictating exactly what can bypass human review and what requires immediate escalation. This JSON output shows what happens when the planner identifies a recurring failure. Here, it noticed a pattern of async rejections and proposed a highly specific fix, adding 3 async await few-shot examples directly to the prompt. Agent 15 operates as a measurable, programmable data pipeline that converts subjective human frustration into explicit, deployable code modifications. Consider a production deployment, a fintech customer support agent answering complex inquiries regarding financial transactions. Over several months, the sensing layer captured a subtle degradation. The agent was retrieving outdated historical documentation and responding to frustrated customers with a tone that was completely mismatched to the situation. Agent 15 aggregated this slow decay. It analyzed the feedback and automatically proposed a structural fix, weighting recent documentation higher and injecting empathy constraints for policy-related queries. We must enforce a hard boundary here. Agent 15 can ruthlessly optimize an objective it has been assigned, but it lacks the capacity to invent its own goals. It cannot bypass the human gate to alter its own core logic or redefine what constitutes a successful resolution. By maintaining that governance, this architecture alters the economics of software maintenance. It replaces the endless cycle of manual debugging with a system of continuous, automated refinement. Agent 15 reverses the arrow of software decay. It ensures that every failure recorded today becomes the precise training data needed to forge a sharper system tomorrow. As the capstone of the software development tier, it takes the verification and validation protocols we apply to data and points them entirely inward, scrutinizing the agent's own behavior. To review the complete LangGraph architecture and access the execution code for the self-improving agent, read Chapter 9 of 30 Agents Every AI Engineer Must Build by Imran Ahmad. True AI engineering requires building systems that refuse to stay the same.